Good morning, everybody. I'm back with my lecture video series on compiler is fun. We have already seen two lecture videos on intermediate code generation. One was on simple arithmetic expressions, and the second one was on simple Boolean expression and very simple statements. We'll revisit those statements again because if you remember, I told you that the if-then else statement was not quite right, the grammar was not quite right, the translation was not quite right, but it was suitable for that purpose. The purpose was to introduce backpatching to everybody. Today we'll be dwelling on actually a few three different kind of lecture videos. So it will be basically a little longish record compared to my earlier records. Let me see. That is because today's lecture has a continuity in terms of the examples. So we'll look at the compound Boolean expressions, the loop statements, and compound statements. So compound Boolean expressions are, you can assume it is like some condition and another condition, or some condition or another condition. In fact, if we understand them, then any combination of that would be very easy to understand. So let us go to a very simplest compound, condition. Mixing or and x less than 5 or x greater than 7 and x less than 9. So if I generate the free address code of this particular conditional expression, I get 6 statements, 2 each for each simple condition x less than 5, x greater than 7 and x less than 9, as we have discussed in our previous lecture video. X less than 5 will give rise to if x less than 5 go to somewhere. Second one will be unconditional go to. Third one will be if x greater than 7 go to somewhere, and 4 would be go to some place. 5 would be x less than 9 go to, and 6 is unconditional go to. If I look carefully in this, then we'll find out that if x less than 5, then the entire condition is true. So then where do I go depends on the conditional statement that I have. Whenever this condition is true, wherever I need to go to execute the next statements, that is where I have to go if x less than 5, or in the other case, x greater than 7 and x less than 9. So if x greater than 7 happens to be true, then I need to go to the statement where x less than 9 is visited. So therefore I go to 5. So that is known. But if x is less than 9, then I know again that the condition is true because already x is greater than 7 and then x is less than 9. So I have to go to wherever I need to go if the condition is true. So line number or statement number or quadruple number 1 and 5 are the go-tos to a target where the control has to go in case the condition is true. So 1 and 5 contain incomplete go-to statements, and they are part of true list of the entire compound Boolean expression. Now 4 and 6 are go-tos which should be filled up with the target where the control should reach in case the condition is evaluated to false, and then wherever control should go, that line number should be used to fill up the incomplete go-tos in line number 4 and line number 6. So false list of this entire compound expression would be 4 and 6. I hope this much is clear. This has been already discussed in my earlier lecture videos on very simple Boolean expressions. So listen to this carefully again when you learn about it. Understand that x is less than 5 makes the condition true. Otherwise, there is one more way to make the condition true, and which is x greater than 7 and x less than 9. So if x greater than 7 and x less than 9 both are true, then I come to line number 5. So line number 1 and line number 5 are the exits in case the condition is true. And line number 4 and line number 6 are the exits where I come if the condition is false. Like if x is less than 5, I come to 2 naturally, then go to 3, right? Now if x greater than 7, then I know for sure that x is less than 5 and x is also less than 7, and therefore it's a complete failure of this condition. So I need to go to the false target of the condition as a whole. Similarly, in case x is greater than 7 but x less than 9 does not hold true, then again the condition is false, right? And then I know that I have to go to the false exit of this particular compound statement. So what will the parse tree look like? The parse tree will look like this, and understand that I have a marker because you have already noticed that this incomplete sentence go to dash is corrected by 5 when because I know that if this is false, then I need to come here, and if this is true, then I need to go to the beginning of this particular statement. So you see that if I know that the first part of this is true, then I know the entire statement is true, and if not, then I know I need to go to this particular statement, to this particular condition checking. So these two M's are for are marker. They will remember the next quadruple number, right? So you just look at the parse tree. This is the complete parse tree, and we will talk about the semantic actions in a while. Look at the parse tree, however, you can understand that this will be my first this will be my first reduction, then this will be my next reduction, this will be my third reduction, this will be my fourth reduction, this will be my fifth reduction, and then the entire thing will be my last reduction, right? So you'll see that we'll go in that manner. Now, when you come here, then the reduction rule that I'm using is this id less than number. So what is the current quadruple number? 0. So what is next word? 1. What is next word plus 1? 1. So e dot tl and e dot fl becomes 1 and 2, right? And what is written next? If it goes to if statements, those two go to statements. So you see, then comes 1 and 2, and these two lines are generated. So the first reduction is complete. This part of the code is generated. This semantic action is taken, and then we go to the next level. So what is the next one? Next one is this reduction. Will any line be generated here? No. No lines will be generated. But this will remember what is my m dot quad is, because that's my reduction rule. So m dot quad, m dot q will remember next word, which is 3. Meaning that the whole that this entire parse tree, the code for this entire parse tree will start from line number 3. Clear? So now we go to the next reduction, which is this one. A similar reduction. First, e dot true, e dot false will be calculated. What are they? They are 3 and 4. This is 3, but that does not mean that the current quad has increased, right? The current quad remains at 2. So next quad will always give me 3, and this will give me 4. And then these two conditional and unconditional go-tos. So what it will look like? It will look like this one, right? It will look like this one. This will remember 3, this will remember 4, and these two lines will be generated. Now comes this thing. Now comes my reduction like this, right? My reduction like this. So what I use is I use the same, the same semantic rule, and my m dot quad will now be 5. Why? Because my current thing is actually 4. So my next line will be 5, right? So you can see that my m dot q is now 5, which is this one, and I go to the next reduction, which is this one, which is this one. So again, E dot TL will be 5, E dot FL will be 6, because they are next word and next word plus 1. And then these two lines will be generated in line number 5 and 6. So it will look like now this one. Now we are ready to reduce this part. We are ready to reduce this part. Right? Therefore, we are looking at this part of the code. Correct? We are looking at this part of the code. Because for this E, only this much code was generated. So I can see that if x greater than 7, then they should go to 5. Why? Because 5 is the beginning of this particular parse tree. Right? So let's see what the code is. The code says E1.tl, that is this TL, has to be completed by this m.q. So that means line number 3 as an incomplete goto whose target will have to be corrected by 5. Now this is true list will remain E2.tl. That means its true list will be 5. See, 3 has already been taken care of. So 3 is not incomplete as of now. But this E can can be false when the control goes to line number 4 or line number 6. Why line number 4? Because x greater than 7 is not true. Why line number 6? Because x greater than 7 is true, but x less than 9 is not true. So therefore, my E dot TL will be 5. See, E dot TL will be 5 because this condition, if this condition is true, then x greater than 7 is true and x less than 9 is true. E dot FL is 4 and 6 because in 4, x less than 7, x greater than 7 is false, and in 6, x greater than 7 is true, but x less than 9 is false. Right? And then I am ready to do this reduction. This particular reduction I am ready to do. The entire reduction. Now this is an OR. So this is predictable now, right? OR means if this condition is false, then you can go to check this condition, right? So E dot FL has to be filled up by M dot quad. So what is E dot FL? 2. So that will be filled up by 3. You see, E dot FL has to be filled up by 3. Yeah, E dot FL has been filled up by 3. Right. E dot FL has been filled up by 3. And what is E dot TL? This is an OR condition. So wherever this condition is true, that makes the whole condition true. And wherever this condition is true, that makes the whole condition true. So 1 and 5 are the true exits from the condition, the whole condition. So 1 and 5 becomes E dot this E dot TL, and E dot FL becomes E2 dot FL, which is 4 and 6. So therefore we get this part. Right? So that is the whole story of parsing the condition x less than 5 or x greater than 7 and x less than 9. That will generate this particular quadruples. Unfulfilled go-tos are there in 1, 5, 4 and 6. 1 and 5 are the incomplete go-tos where from I should go to the true exits, and 4 and 6 are the incomplete go tos, where from I should go to the false exits. So once this is done, we'll be going to next statement, which is interesting and which is flow of control. We'll basically look at while statement, the loop, the first loop statement will do, I think. I mean, no, the first is we'll have a look at if, then, else, else. And understand that in a compound statement like this, I mean, one S will be followed by another S, that S will be followed by another S, S will be followed by another S. So if you look at the parse tree, this S will have its parse tree. That parse tree will have a number of incomplete go-tos. Those go-tos will have to be filled up by the beginning quadruple number of this second block. So I have to backpack. So I have to incorporate two things. One is s.nl or s.next list. So wherever I have s1.next list, they have to be filled up. They have to be filled up by this 200, because 200 is the beginning of the second block, right? Similarly, 300 is the beginning of the third block. Therefore, s2.next list, all the incomplete go-tos in s2.next list must be filled up by 300, correct? So this is the way I have to backpatch the next list of any statement to the first line number, first quadruple number of the next block of statements. So remember this. This will be very handy. Understand that we have an additional attribute in S, which is s.nl, and similarly L is another non-terminal used for compound statements like begin and end, like your in C opening brackets and closing brackets at these begin and ends. So within begin and end, a block exists which is separated by a semicolon. So this L is responsible for generating compound statements. So it can generate only one statement, or it can generate a series of compound statements separated by this semicolon. So let's see the first statement, which is if E, then M1 S1 N, else M2 S2. In the entire thing, I mean, you just find out that I've done this. I mean, in the entire remaining part, this N and M are interchanged. That does not change much of a meaning in this particular case, but in certain cases they will. We'll assume that they will not have any difference in meaning as far as this particular example is concerned. But it will be handy and it will be better if you change the N and M here and do the remaining stuff once again. So if this is the parse tree of the if and else. Now, if you remember, if you look at it, I'm using a very simple condition here, which is maybe x less than 5 kind of a thing, and therefore the first reduction will be here, right? The first reduction will be here, and the second reduction will be here, right? And the third reduction will be M, will be here, and the fourth reduction will be here. In fact, it is not the fourth reduction. The fourth reduction, yes, this is the fourth reduction. So and so on. We'll go on doing these reductions and applying the semantic actions as we go along. So let's see. So first is this reduction, as I said, and we know that the semantic actions, we have already come across the semantic actions. I need not repeat that. Two statements to generate the attributes, to fill up the attributes of this E, and two more statements to generate the go-to statement. So it will be something like this, that TL is 1, FL is 2, and TL is 1, FL is 2, and these two lines are generated. And then I come to the reduction of M produces epsilon. So where m dot q is set to the next word. What is the next word? Next word is 3. So I remember the next word and I go to the next reduction, which is this one. And we all know that in this reduction, nothing will be generated, but the semantic action will take place, which is e dot val equal to 5. And then this particular statement will be taken care of, where one line will be emitted, that is a is equal to a is assigned 5, and then the next list of s will be set to none. Next comes this one. Again, I mean, you should better do n first, m next. Doesn't matter now, but will matter later on. So once I do that, basically m dot q is set to 4. And then again I go to n produces epsilon, and n dot nl goes to 4. But nothing is generated in the output. Now next reduction will be here, where e dot val will be set to uh, I think 6. Yes. And then the next reduction, where the next one sentence will be generated like this, and the s dot nl, that is this ssnl, that is this ssnl, will be generated, will be set to null. Once that is done, I come to the final conclusive statement, which is this is very interesting. This is for the what? This is for the if then else. This is for the if then else, and if I'm not wrong here, in this and yeah, here I had a go to somewhere, no, missed it somewhere here. Yes, this n dot nl is just not n dot this direction just not makes n dot nl to the next word. It also emits this go to. Why? We know, because we know that in case this condition is false, in case this condition is false, then control must not come here. Control must not come here. Control should go beyond the block where the code for true exit is written. Here control should come, or here control should come to absolutely this place, right? Right? So therefore, we have to write that go to, otherwise we'll make a mistake, the same mistake which we actually made in our previous lecture on simple conditions and simple conditional statement. So this go to was missing there. So once this go to is done, then the assignment statement is done, and then I come to this particular place. Now you see, if this condition is true, where do I go? I go to this S, right? So how do I know where is this S? I know because E dot TL contains the incomplete go to, right? And where does the first statement start? Remembered by this M. So I go to 3. So that is my first backpatch is done. Then my next backpatch, what is that? If the condition if is false, then where should I go? I should go to this statement, right? This is if this condition is false, right? If this condition is false, right? And this is this statement is in case this expression is true, then I come here. In case this expression is false, I come here. Therefore, the true exits are to be filled up by this m dot q, and false exit is to be filled up by this m dot q, right? So that is what it is. And then I understand that there is one go to which is remaining. Why this one go to is remaining? Because of this n dot nl. So s dot nl does not have any incomplete go to. This statement does not have an incomplete go to. This code does not have an incomplete go to. But I mean, this s generated this statement, right? This statement, right? This s generated this statement, and this s generated this statement, right? Right? And therefore, they do not have any incomplete go-tos. But this 4 has an incomplete go. So this SS next list must contain this SS next list, this SS next list, as well as this ends next list. So both of them are null. This is null and this is null. So S dot NL will become only. That is why S dot NL is. And it remembers that in the next line after this if then else statement will be starting from 6, because that's where the things stand. And if in case this 6 is known at some point of time, what should be what go to should have target as 6? The line number 4 has a go to whose target should be 6. That is the whole story of this next list. We'll see this working again in another example when we talk about compound statement. So next is our loop statement, which is while do. So you see that in while do we have many markers. Before this expression, I need a marker. Can you tell me why? See, this S1 will contain some statements. Once they are done, where should control go to? The control should go to from here to here, right? Right? Because that is good. That is while do. You have to come back. So from here, you have to come back to here, right? And in case this condition is true, where do you go? You have to come to the beginning of this statement, the statement where S1 starts. So these two backpatches will be required. These two backpatches will be required, and therefore, so you see, so S1 backpatch S1.nl by M1.q. You have to emit some go-to which will be filled up by M1.q, and E.tl, if E is true, then its true exits must be filled up by M2's quantum. Right? So let's take an example. Please note that I am taking this particular condition. This condition is special. Why? Because in our example, I have just done this example, this condition, already we have done it. So when I talk about this condition in this while loop, I will be very concise. I will not explain it at all, because this has already been explained in the first part of the lecture video, this lecture video. If you want to know more about that particular part 3, you can always refer back to that particular part 3 and come back to this particular slide once again, if you so like. Therefore, I wrote like while M, E, M, S, and S is ID is equal to E, and E produces num. But see that this part of the parse tree I have not written. Why? I mean, after all, this E, I mean, I know that, right? I know that once this particular parse tree, once this particular parse tree will be, will be worked out, this particular parse tree will be worked out, then this is outcome. These 6 lines will be generated. All these 6 lines will be generated, right? And TL, E.tl will be 1, E.fl will be 2, right? And these are wrong. This E.tl would be this E.tl would be 3, and this E.tl will be 4, right? And so this is all done. In fact, I am not looking at this part of the parse tree at all. This part of the parse tree I am not looking at all. This part of the parse tree I am not looking at all. I am looking at this part of the parse tree. I am not looking at this part of the parse tree. This part of the parse tree I am not looking at. This is unknown for me. Once you do this, these 6 lines will be generated, and this TL will be calculated and this FL will be calculated. We have already seen that. So our journey begins from here. So first, I mean, even this m dot q is equal to 1 because I know that client line number was 0 and m dot q was set to the next code, which is 1. And then I come to this, this particular reduction. This particular reduction. I come to this reduction, and when I come to this reduction, basically m dot q becomes 7. Now I come to the next reduction, which is e produces num, and which is e dot value equal to 7 or 6, whatever, and then I write line e equal to 7, and then this is my while statement. So generate. I do backpatch s1.nl, s1.nl is empty, nothing to do that. E dot tl is empty dot q. I therefore e dot tl is 1 and 5. I make them go to 7. M2 dot q. E dot tl 1 and 5, 1 and 5 changed, go to is changed by M2 dot q. S dot nl is E dot fl. So I remember the next list for S dash. I emit a go to where? Go to the beginning of the expression. Where is the beginning of the condition? I remembered here. So this m dot q is filling up the target of this go to. See, this is a fine routine for a while loop. Right? Next comes a compound statement. So we are not looking at this now anymore. We are looking at this particular thing. And we are looking at this. We are looking at this. We are looking at this. So let us go and see. So our statement 2. This one, see, this one we have already done. This statement was already done. Similarly, this statement was already done, right? And therefore, the parses for this statement and this statement are known to us. We'll use that in our discussion. How? Let's see. So our parse journey begins like S begin L end. Very nice. Then comes my journey for L. L produces L semicolon M S. Very nice. Then L produces S. Now you see S semicolon S end, and beginning and started with begin. So what is the thing that I have now? Begin S semicolon S end. Right? And after this begin, what is there? While loop. After the while loop, what is there? A conditional statement. If then else. So I know that this S will produce, these 6 lines. These 8 lines. These 8 lines are produced by the while loop. Why? We have already seen that. This is what it is. So therefore, I simply can take that. And after all, if I do that, this will only come. I have these 8 lines. I have S dot nl is equal to 4,6. For that matter, this part is also not relevant for us because we have done this, right? We have done this only after that we got these 8 lines and this S dot nl is filled up. So we remember that, and not only that, this S is produced from L. So I remember I have a production rule like L produces S. Only one semantic action, L dot nl is equal to S dot nl. If I do that, then my L dot nl is equal to 4,6, and I come to generate my M dot q is 9. Why? After all, m dot q, this m produces epsilon. This particular semantic action was taken before the semantic action for this s was taken. So at that point of time, current quadruple number was 8 up to this, the end of the while block. And then if I find out the next word will be 9, and therefore m dot q is 9. Now we know that if we generate this particular parse tree, then I generate 5 lines. Again, this I know because I already have done this. S produces if E, then M S, M else N S. We have done that. So the only thing that will change is E dot TL will not be 1 and 2, it will be 9 and 10. S dot NL will be null. M dot NL will not be 4, but it will be 12. M dot Q will be 12, and this M dot Q, that is before this statement, will be 11. So if I do that now I see that this is my grammar. This is my grammar. So what is the semantic action? It is L semicolon MQ S. All 12 lines, all 13 lines are already done. But why S dot NL is 12? Because I know that this SL has an incomplete go-to in terms of 12. Right? So while loop is complete, then in if then else, if x less than 5 is not true, where to go is not known. Where to go? After the if statement, right? That's where you have to. So what we do is L1's next. What does that mean? That means L stands for this first L stands for basically up to this. Up to this was generated from this L. From this L, this part is generated. Now, 4 and 6 contains go-tos whose target is not known. What will be target? If the while condition is false. If the while condition is false, which are the lines that detect that? That detect line number 4 and line number 6. How do I know? I know that for sure because L.NL is 4 and 6. So what should be the targets of these go-tos? The targets of these go-tos will be the beginning of the if then else statement. So make them 9. Make them 9. And whatever is still remaining in S dot. So these are taken care of. These are taken care of. Whatever is remaining in S dot NL, you have to carry it forward to this S. This is. So you have to remember that this is what the entire code, and you will remember that S dot NL is equal to 12. So that is the final thing. So you see that I have talked about in this lecture video parts 3 of a compound statement, the semantic actions in a compound statement like if then else. I told you about a compound expression x less than 5 or x greater than 7 and x less than 9. I talked about the if then else statement. I talked about the while statement. Then I took both these while statement and the if then statement in a begin end block. And for that also I generated the tree address code. By that I tried to explain to all of you how the semantic actions are executed. What are the semantic actions? How they come? How they appear? I mean, I did not tell you what the semantic actions are. I said that this is a situation. I need to do this. What actions I should take? Right? So look at the situation. Look at the tree. Look at the parts. Look at the generated code, and see that this is my reduction step. What can I do at this reduction step? Whatever I can do at the reduction step to remember the parts that is beneath, as well as that can be done right now. Those are my semantic actions. So the semantic actions were not told to you at the beginning. I give you the situation, explain the situation, and then ask you to think about the semantic actions. And the semantic actions appear intuitively. That is how we have to think for triad code generation or intermediate code generation for any grammar. You cannot remember, you cannot memorize the triad codes. That is not the way to learn a subject. You think about the examples. You take it as a problem. Solve the problem by whatever you know. Build on your knowledge. You have some knowledge, and then build on it. Get the next level of knowledge. Then again, you build on the next level of knowledge to get the higher level of knowledge. That's how you build your whole knowledge, right? So I took in 4 examples in this lecture video. They are all connected together. That's why I could not, divide it into halves. And that will be kind of quite enough for you to ponder about all kind of statements that we have in a programming language, except the declarative statements. Other than the declarative statements, all statements are done, and therefore I would consider that the three underscore generation for programming language kind of a grammar is all done, right? So thank you very much for listening to my video. I hope that you learned. More than that, you learned learn, how to remember instead of memorizing things. If you can do that, that is the best thing. As I said, go on practicing. What you will practice? Go on practicing for the known grammars. Go on taking examples. Draw the parse trees. Find out the reduction sequences. In the reduction sequences, find out what is logical to be done, so that if the parse tree is obliterated, erased, then you do not need to go back to the parse tree again. And what can you do in the code generation part so that you are better off? So think about it and then write down the semantic actions. It will be natural. The actions will never required to be memorized. You can simply tell what they are. And for a new grammar, generate the grammar rules first, then find out what are the attributes that you need to add. Of course, with the grammar, generate the parse tree. And when you go on reducing one after another, find out what attributes are required in the non-terminals to remember that parse tree beneath it. And what are the outputs that are to be generated when that reduction takes place. And remember, reduction will take place and the code will be generated in a sequential fashion. Other than backpatch, you do not have any other rule as of now by which you can jump to previous statements and do something else. In fact, nothing is required, because your statements are such that only go-tos are there which can be incomplete. Other three address codes that we have, have to be complete. So only conditional and unconditional go-tos can remain incomplete, and then they might require to be remembered. They might be required to be remembered. You remember them, and at suitable points of time, you actually fill them up by backpatching. So with that, we come to the end of three address code generation of non-declarative statements as a whole. We'll go to a basic of code optimization in my next lecture video, and after that I'll continue to upload lecture videos for more advanced topics as time progresses. Thank you very much for your patience.